Hello everyone, my name is Camille Dupré and I'm here to present my work, TriPad, Touch Input in Augmented Reality on ordinary surfaces with hand tracking only. This work was done in collaboration between the Hilda Inria team and the company Berger-Levrault. When interacting in augmented reality, mid-air input is generally favored over motion controllers as it leaves the hand free. But it has limitations as it causes fatigue, lacks haptic feedback to confirm input actions, and has limited motor precision. Physical surfaces have the potential to improve that. As they provide haptic feedback, they can improve input precision and reduce fatigue. Previous work tackled how to use passive surface as support for touch input, and it can be achieved in different ways. It is possible to use stationary setups with sensors in the environment, but also to use wearable setups with sensors on the user arms or sensors already embedded in AR headsets. However, all of these solutions present limitations. When designing our technique for opportunistic touch input for augmented reality, we established a list of requirements that it should meet. It should work in a variety of environments without needing to add additional sensors, neither on the environment nor the user. We wanted our technique to be very easy and quick to set up and use, while enabling direct and indirect input to limit fatigue and give more flexibility to the user. Finally, we wanted something that requires only minimal computation. So we introduced TriPad, a hand-centric approach to turn any passive surface into a touchpad. Users create a touch surface with a simple on-tap gesture. Our approach is based only on tracking the movement of 3 fingers, from which we infer the position and orientation of the plane. TriPad works on a variety of flat surfaces, no matter the orientation and the material. It even works on perforated panels or windows. Instead of interacting in the air, if the virtual content is not anchored to a specific world position, TriPad can be used to move the content on top of a physical surface and then interact directly with it as on a tactile screen. To enable this kind of interaction, we needed to be able to detect click and drag events. But in some cases, the virtual content cannot be moved. Then, TriPad can be used for indirect interactions, like a trackpad, allowing the user to interact in a more comfortable position and reduce fatigue. To differentiate a left click from a right one, or a drag and a move event, we added 2 gestures to our vocabulary. As one of our requirements was that the technique should work on different materials, we first tested it on 3 common materials: drywall, glass, and wood. We recruited 12 participants for a within-subject design, and each participant had to perform different actions to check the robustness of the recognition system on different materials. We observe a high recognition accuracy overall and get positive feedback supporting that our TriPad recognizers work on various common surfaces. Only one condition did not meet the threshold. The move events were sometimes recognized as contact click events. Thanks to this observation and the feedback we got from participants, we refined the design for those gestures. Now that we have seen that it technically works, the next step is to compare its performance to the baseline, but also to see if there is difference between a pad on an horizontal surface and a pad on a vertical surface. Again, we recruited 12 participants for a within-subject design, and we evaluated 2 tasks, a pointing and a pursuit task, at 2 interaction distances, near and far, with 3 interaction techniques, horizontal tripad, vertical tripad, and the baseline. Our hypotheses were first that tripad indirect techniques are less tiring and more precise than the baseline because it benefits from haptic feedback, and that a horizontal tripad performs better than a vertical tripad thanks to user familiarity with trackpad. To assess the performance of the technique, we compare them in terms of speed and accuracy. For speed, during the pointing task, participants were faster with tripad technique than with touch, while they were equivalent or a little bit slower with tripad than with the recast. For accuracy, during the pursuit task, participants followed the target with more precision with touch than with the tripad, while they were more precise with tripad than with the recast, showing a good speed-accuracy trade-off for tripad over the different conditions. We also collected feedback through questionnaires. In terms of fatigue, tripad were perceived as less tiring than direct input, especially the horizontal one. This condition was also generally preferred by participants over the 2 other conditions. It may be explained by the user's familiarity with trackpad and mice. 10 participants out of 12 spontaneously state that the horizontal tripad was like a mouse, whereas only 1 participant made this analogy for the vertical tripad. Our observation supports the first hypothesis. Tripad techniques present a good speed-accuracy trade-off while reducing fatigue over common mid-air interaction technique. However, our findings are more nuanced regarding the second hypothesis. The horizontal tripad outperformed the vertical one for the pointing task, maybe because participants are very used to pointing tasks with trackpad, but they are less used to pursuit tasks. So in that case, the vertical tripad performed better than the horizontal one, probably because the pad and the screen shared the same orientation. To conclude, we introduce the tripad concept. We show that our hand-centric approach works on a variety of surfaces, even windows and perforated panels. It presents a good speed-accuracy trade-off for interaction while reducing fatigue over mid-air interactions. To go further, it would be interesting to investigate ways to increase tripad expressive power while keeping the approach fully hand-centric. For instance, we could use information from both hands, like their relative position or orientation, for example, to create different types of pads, such as a keyboard or a drawing pad. Information from both ends could also be used to interpolate simple concave or convex surface. Thank you for your attention.